Okay, we're going to do a few examples that will allow you to be able to identify intermolecular forces in different compounds and to also connect those to boiling point trends. So our first example comes from lecture 2025, and it deals with identifying intermolecular forces in different compounds. So we're going to identify different intermolecular forces in a series of compounds, and our first compound is BF3. So the first thing you're going to want to do if you're not sure about the structure of a compound is to draw a Lewis structure. So I'm going to draw a Lewis structure, and I'm going to draw a geometrically accurate Lewis structure. Okay, so there's our Lewis structure for BF3. So the first intermolecular forces you should always be able to identify are London dispersion forces, or just simply London forces. All molecules or atoms will have London forces because all atoms and molecules have those instantaneous and induced dipole interactions. So the second thing you would like to check is to see if a molecule is going to be polar or not. And BF3 has a trigonal planar geometry. All of the boron fluoride bonds are equivalent, so you can draw these bond dipoles that will point towards the fluorine, since those are most electronegative. And because of the geometry, the trigonal planar geometry, those bond dipoles will cancel out, so we would expect BF3 to be nonpolar. That means that we won't expect BF3 to have the dipole-dipole interaction since it's not a polar molecule. In addition, since BF3 has no hydrogens at all, so would have no hydrogen to fluorine bonds, we would not expect boron trifluoride to have hydrogen bonding. So the only intermolecular forces present in BF3 would be London dispersion forces. So we just have our London forces. Okay, so that's BF3. Our next example here is isopropanol. I will draw a Lewis structure for that. Isopropanol. It has the following Lewis structure. Okay, so that's a bit complicated compared to other Lewis structures we've drawn in class. So you would expect that if I wanted you to talk about the intermolecular forces for this molecule, that I would actually draw it for you or give you a drawing of the Lewis structure. So once again, we're going to identify the intermolecular forces in this compound. So for isopropanol, we're going to have, of course, London forces because all molecules have London forces. Okay, so the next thing you want to check is to see if this molecule is polar. So we certainly have a polar bond. So the oxygen-hydrogen bond here, the OH bond, is polar, a polar bond. But will the whole molecule be polar? Well, it's hard to decide, but take my word for it. Isopropanol is moderately polar, or mildly polar. And again, for exams, I will give you an example where you'll be able to very much tell if a molecule is polar. Usually we'll stick to small molecules. So since isopropanol is polar, or at least slightly polar, polar molecules will also have dipole-dipole interactions. In addition, isopropanol has an OH bond, a hydrogen that is bonded to a oxygen. So because of that bond, we will expect isopropanol to have hydrogen bonding. So we have 3 different types of intermolecular forces that are available for isopropanol. Okay, our next example is hydrogen iodide. Or HI. Very simple Lewis structure. Okay, so we're going to identify the intermolecular forces in hydrogen iodide. So, of course, all molecules have London forces. Okay, so we'll see if hydrogen iodide is polar. So this one's a little bit iffy, but so you would need to consult electronegativity differences. It turns out the electronegativity difference, if you remember we talked about delta chi values, is about 0.4 electron volts. So this does mean that hydrogen iodide is in the low range of being polar. So it is polar. So we would expect HI to have dipole-dipole interactions. Okay, and since the hydrogen, this is a hydrogen iodine bond and not a hydrogen fluorine, hydrogen oxygen, or hydrogen nitrogen bond, we don't expect hydrogen iodide to have hydrogen bonding. So the only 2 intermolecular forces that's present are London forces and dipole-dipole interactions. Okay, and our final example, I will just write here, is krypton. So krypton's a noble gas. Should remember that from our periodic table. So being that it's a noble gas, not a molecule, we wouldn't expect it to have dipole-dipole interactions or hydrogen bonding. However, krypton does have London forces, which might be confusing to some, but any atom, atomic substance such as a noble gas, since it's an atom, it has an electron cloud that can be distorted, so you can't have the instantaneous induced dipole interactions when 2 krypton atoms are next to one another. So we would expect noble gases to have London forces. And a good indication that noble gases have London forces is most of them can be liquefied and also solidified, so frozen. And that can only happen if there are interactions between the atoms, and the only interactions you can have for a noble gas would be the London forces. Okay, so that's an example of identifying different intermolecular forces in different substances.